Okay, let's talk about elements, compounds, and chemical formulas. One of the things we want you guys to be able to do is understand what chemical formulas are telling you about a chemical compound or a pure element. So the nature of materials. Let's start with that. In nature, things are rarely pure. You usually get a mixture of things. Sometimes you can get a mixture of pure substances, sometimes you get a mixture of compounds. Or I should say, sometimes you get a mixture of elements, sometimes you get a mixture of compounds. But whatever it is, it's typically not pure in nature. However, if you purify it, typically it's going to fall into the category of either an element, which has only one type of atom in its chemical formula, and then, let's see, a compound which has more than one type of atom. So notice, one type of atom, and although there's two atoms, it's still one type of atom, one type of atom, one type of atom, one type of atom, which is contrasted with more than one type of atom, more than one, more than one, more than one. Okay, so that's the difference between element and compound. Now, there is this also little blurb here. All elements above number 92 are artificial. Element 92 is uranium, and then anything above that is radioactive. And actually, 92 is also, there's many radioactive versions of this, but everything above that is radioactive and typically only produced in a lab. It is produced in nature, but it doesn't last very long. So that's why we don't find it around. So the only ones we have to find above this are the ones made in a lab. Now, a compound, again, beware that just because there's a 2 or 3 or whatever in the chemical formula doesn't necessarily mean it's a compound. You have to understand, you have to count how many types of atoms are there. Now, names and symbols for the elements. Each pure element has a name and symbol. So the symbol's always either 1 or 2 letters. There's no 3-letter symbols. Some of you may have an old periodic table that has that, but those are just temporary placeholders until they come up with an actual name for the element. So you'll always find either 1 or 2 letters. The first letter is always capitalized. The second letter is always lowercase. And that's actually a big deal because this, capital C, lowercase o, is very different from capital C, capital O. This is cobalt, a shiny metal. This is carbon monoxide, a poisonous, clear, colorless gas. Odorless, too, for that matter. So capitalizing versus not capitalizing completely changes the meaning of what you're looking at, and it's very important to make sure that you are doing that properly. When you type into a digital form, H2O is different from H2O, and I guess like oftentimes it'll be reflected as like this. H2O will be the right answer for many questions on your test. If you type H20, you're getting a 0 for that question. So make sure that even though things might look similar, make sure you're selecting the right things and typing properly. Because, for example, if a question had cobalt as the right answer and a person typed carbon monoxide or lowercase c, lowercase o, this would be right, this would be wrong, this would be wrong. So you got to make sure to capitalize or not capitalize properly. So symbol typically converts of the first 1 or 2 letters of the element's names, or typically consists of the first 1 or 2 letters of the name. So O for oxygen, Kr for krypton, for example, but that's not true for all of them, and I think there must be further on that I had examples of that. But subscripts indicate the proportions of elements in a compound. So first of all, this isn't a compound, that's a pure element composed of 2 hydrogen atoms stuck together. This is a pure element of just 1 potassium atom because they don't bind to anything, they just all hang out together, but they don't literally bind to each other. Gold is just atoms sticking around, not bound to each other, but just atoms just sticking around. So pure element, pure element, pure element, this is a compound, and this means that there's 2 hydrogen atoms for every 1 oxygen atom, or this means 6 carbons for every 12 hydrogens and 6 oxygens in that, bound together in that compound. Now, sometimes there's a total mismatch between the name and the symbol because it comes from another language, like AU for arum from the Latin language, and then PB for plumbum, which, by the way, this is why we call plumbing what it is, because plumbing comes from the Latin word for lead because the Romans made their plumbing, as in like their pipes and stuff, out of lead. So there's plenty of other examples, like K for potassium because it's from the Latin kalium, Na for sodium because it's from the Latin natrium, various others like that, or tungsten is W because it's from the German Wolfram. So others are named after places or people. Californium is an element discovered at UC Berkeley, so that's why it's called this, or Einsteinium is named after Einstein. He had nothing to do with it. They just named it after him because he's famous. But regardless of all those things, Dalton's atomic theory talks about these atoms and talks about certain things that are true about them. So when we study all these atoms, the potassiums, the sodiums, the Einsteiniums, the leads, the whatever it is, there's certain things that we notice as a pattern between all of them. And this goes back to Dalton, an English scientist who did his work back in the early 19th century. And his theory turned out to not be 100% right, but it still forms the basis of what we do, because all elements are composed of atoms. That's right. All atoms of a given element are identical. He didn't know about isotopes, but he was more or less right. Atoms of different elements are different. Okay, so a gold atom is different from a silver atom, for example. And then that's consistent. It's in all situations. Compounds consist of the atoms of different elements. So in other words, yes, if it's a compound, then there's different kinds of atoms stuck together. And then atoms are neither created nor destroyed in a chemical reaction. So these ones are completely correct. This one's partially correct. He didn't know about isotopes. You probably don't know what an isotope is either, but you'll find out about that in the future notes. Now, chemical formulas. We need to understand what they represent. People will fall for the wrong question all the time. We'll ask you, what does a chemical formula represent? That will be on a quiz. And people will say it represents the number of atoms, which is wrong. Chemical formulas are a ratio, not a total number. So, if you have a bag of sugar, it does not contain a total of 6 atoms of carbon and 12 of hydrogen and 6 of oxygen. It contains a ratio of 6 to 12 to 6. Now, why don't we just reduce it to 1 to 2 to 1? It's because it tells you the total number in each molecule, but it doesn't tell you the total number in the entire substance. So it's still a ratio. So I know what I just said may have confused you between talking about the total number in a molecule versus the total number in a substance. If that's confusing, don't worry about it. Just remember, it represents the ratio of atoms present in a sample. So this represents in an entire sample, like say a bag of sugar. If you hold that bag of sugar, the actual number of carbon atoms is a number so big you don't even name for it. It's a number that you probably need about 30 or 40 zeros to write. Same for the number of hydrogen, same for the number of oxygen. So it doesn't work to write the total number because atoms are tiny, so if you have enough to see, it's a gigantic number. So what that means is we just do the ratio of how they compare to each other. So, rules for writing formulas. So you will be writing lots of chemical formulas. Let's look at the rules. Each atom present is represented by its symbol. The number of each type of atom is indicated by a subscript. That's these numbers here. Sub means like below, and script means written. So written below is what the word subscript means. Make sure to label it on your own handout, by the way. This tells you 2 sodium atoms. The subscript only talks about the atom that comes before. So this says 2 sodium atoms. See how there's no subscript here, but a 4 here? This 4 is only for the number or the oxygen that's right next to it. So in other words, it's only for the element next to it. This is only for the element next to it, because this is one element right here. This one doesn't have a subscript, which means we assume it means 1. So you never write the number 1 in a chemical formula. If there's only 1 of something, you just leave it blank. That's why, for example, H2O, this means 2 hydrogens, 1 oxygen. We didn't write 1. Or NaCl, table salt, there's 1 sodium, 1 chlorine. We don't write the number 1. But if it's not the number 1, like that H2O example, like there's 2 hydrogens, we got to write any number that isn't 1. And so that happens here too. It's 2 sodiums, 1 sulfur, 4 oxygens. That's what that formula is telling you. You're going to do the same. Make sure to write these as subscripts. We see sometimes people write it like this. Oops, I just wrote that backwards. Do not write them as a superscript. That means something totally different. This is wrong. Don't do that. Okay, make sure when you write your chemical formula, subscripts. Not above, below. Okay, when only one type of atom or only one atom of a given type is present, the subscript is not written. Okay, like I just said, if there's one, don't write the number 1. The number 1 does not appear in chemical formulas anywhere unless it's part of like the number 10 or 11 or something like that. All right, so do not write the number 1 in a chemical formula. So practice writing chemical formulas. This is something that you should be able to do. Just so that you know how it works. If it says a molecule contains 4 phosphorus atoms and 10 oxygen atoms, you're going to assume that it's the same order that I give it to you. So 4 phosphorus atoms, you write phosphorus first. Phosphorus is P. Like you look at your periodic table, find phosphorus, it's P. You look at your periodic table, find oxygen, it's O. So put it in the same order given. It says 4 phosphorus atoms, so you put a 4 down here next to the phosphorus, and 10 oxygen atoms, you put a 10 right here. Don't bother trying to reduce it, it's just leave the ratio as it is. That's a 4 to 10 ratio. All right, so that's basically how you go about doing it. You're going to do the same thing for the rest of these. Go ahead and do that now. And actually, no, before I do that, let's do the next one too as a reminder. 1 uranium atom, 6 fluorine atoms. Uranium is U, your periodic table has that. Fluorine is F, so it's capital U, capital F. And then 1 uranium atom, remember, don't write anything. 6 fluorine, put a 6 there, so you have 6. So go and do the rest of these, and then pause the video now, and I'll put the answers up. All right, there's the answers, and that's it. Happy studies.